Right, hello, I'm Danny. I'm one of the engineering managers here at Sky in God Data. I was going to say that I'm joined here on stage by Chris and Tom, but I guess they'll join me later on. They're two of the senior developers here at Sky. We've got a lot to talk about, so let's get into it. I'm going to give you guys a quick architecture overview of how our platform works. This is to set the context a bit for Tom and Chris and what they're going to be talking about. Tom will then talk about how we use shapeless to enable type-safe dynamic transformation on runtime, and also how using ADTs for error handling helped us gain a 20% performance increase. And then finally, Chris will talk about Chewbacca, which is our akka string wrapper with the delivery guarantees baked into it, which we are eventually planning to open source, hoping that Disney doesn't sue us for copyright infringement. So let's start with talking about proving that we can do 8 million records. So this is a screenshot from our marshalling application, and you can tell that at some point we received the burst in data. The application scaled to ingest 8 million records, and then once we ingest it, we scale down. This just to give a clue of at what level we operate and the scale that we operate at. On the left here, you can see the amount of feeds that are ingested by, it says Gecko here, that's the name of the application, but this is the ingest layer component. And then on the right there, you've got the amount of feeds from our obfuscation and standardization component. They differ because an obfuscation layer can ingest, so you can have 2 of these feeds if you wanted, or 3, ingesting from one of these, and that's why the difference in numbers there. And then here you've got the amount of records ingested in a day, what the amount in a week, and so on and so forth. So, just to give this architecture overview, what I want to start saying is this platform is completely self-serve. So us developers don't need to know, well, them developers, not anymore, don't need to know anything about the feeds that are being added to the platform. If a data engineer needs to onboard a new feed, they can come along, configure it, raise a PR, merge it themselves. We don't need to review anything. We've got tests at PR time that ensure that the configuration is going to be syntactically correct. Merge it, get it deployed automatically, and boom, the feed is in production without us even knowing about it. Obviously, this calls for a lot of flexibility because different feeds and they could have different formats, different origins, and that's why you can see the difference in origins and formatters. We've decoupled the technology from which we're ingesting from the format of the data that we're ingesting completely. So if the data engineer needs to come and onboard a new feed, they can mix and match them as they like. Now, don't ask me why someone would have Kafka in XML format, but they wanted to. It's technically possible. We then ingest this data in the ingest layer here. I think this doesn't work on the Y, or maybe it does. So we ingest the data here. As long as it's a valid JSON, as long as it's not completely incorrect, we transform it into JSON and put it on a pub subtopic, from where the obfuscation and standardization layer will then ingest it. Big simplification here, there's a lot going on. There's also some akka clusters in that bit there, and the obfuscate standardize going on. If we need to join information from 2 different topics, we can do that. Obfuscate means basically complying with GDPR rules. So we obfuscate all the PII data and all of that. And then standardize, which means outputting data in Avro. Obviously, Avro being Avro, we're going to have a schema. So if the original JSON that we transformed cannot be mapped to the Avro schema in the way that we expect, we're going to fail the message and come back to it later at a later stage. This data is then stored into BigQuery and then used from our customers. One of them being personalization, which some of the guys are here tonight, thanks for coming. They are Scala devs as well, and they do some cool stuff too. Feature store, which is another one of our components, some of the devs are here as well. All written in akka clusters. I know very little about this, so if you've got a question on this, I'll redirect you to who knows more. And then finally, what pays the bills, which is the exec reports that are all done in Tableau. We don't really have much visibility of these, but we're told that they're important. Also, one thing that I like to always mention is how the data that we ingest effectively directly affects the share price for Comcast, as it's used to calculate the viewing and the earning reports. So it really has high visibility. Then just to finish, we've got data disaster recovery system. So as some of you may know, the PubSub data expires after a certain amount of time, which is less than what we would want to store it for. So in case anything happens, we also back it up on GCS. And obviously the JSON is raw data, so we're only going to be storing it for 28 days, while in Avro, at that point it's obfuscated, so we can store it for as long as we want. And I think at the minute we've got it set to 5 years, but whatever the business wants, basically, and wants to pay for. Last point on how the platform scales and the operations of it. So this is all deployed in the cloud. Obviously, it's all Dockerized. If we have a certain burst of data, as we saw in the first slide, we can scale as much as we need. It's quite elastic, and it's done on automatic metrics, so we don't need to intervene. It's done. It can be done. So in ingest layer, for example, we're not going to know, because we don't have the metrics on the origins because they're external to our system. So we're going to scale based on CPU usage. While on the obfuscating standardization layer, we know how much backlog we've got, so we scale on the custom metric, which is the backlog size, and just scale as much as we need. Once we've consumed the backlog, we scale down, containing our costs. This is also deployed on preemptible nodes, which is another cool feature of GCP, and if you're interested in that, feel free to come and ask me. So enough with the boring architecture level. Let's let Tom getting into the Scala stuff. So there you go.
Thanks, Danny. I am Tom, senior engineer, same team, responsible for this platform. And first up, I'm just going to start telling you guys a little bit how we use shapeless to have type-safe dynamic transformations in the obfuscation standardization app. Shapeless is a sort of type class dependent, type-based generic programming library for Scala, if you're not aware. And a lot of benefits are listed here, so you can help to reduce boilerplate code for handling types. It lets you allow specific set types. It's similar to what we've done at the bottom here. I'll explain. Allows the use of polymorphic functions on certain generic types, and it keeps all the access to built-in functions for case classes and things that you have, which you normally lose if you go to sort of typecasting and edit any type. So at the bottom here you can see a co-product type that we have called transformable, and it can be one of string, long, double, boolean, or a list of strings. And this is just the definition of one of the feeds that Danny outlined earlier. Ignore the source destination schema for now, those Chris will cover later on. But what I want you to focus your attention on is the fields object. And from there you can see we take from a JSON data field, source field A, through transformation called size of, and it will end up in an Avro destination field 1. Similarly for destination field 2, that comes from source field B, and we'll go through an uppercase function. So how does that look in the actual transformations themselves? The top is a little extract of just a small function we have that actually extracts a specific type from that co-product type, and if not, wraps it in an incorrect type exception that we can deal with later on. And the bottom is actually a kind of brief example of one of our transformations. So here we're extracting from the input transformable a string and just uppercasing it and returning it with some context object that's not really relevant for this part, but that's kind of how we can have type-safe dynamic transformations. If we wanted to have the ability to deal with multiple types in the same transformation, say for something like size of here, we could define a polymorphic object similar to this as size m, which can have different definition cases on how to deal with specific types. So we can see we have a case for an integer, a string, and a boolean here, and they do different things with those types based on whatever we want really. So the integer just returns itself, a string returns the length of it, and a boolean just returns a bit 1. The way that that's used in a transformation is just this simple one line here, you can map it through the polymorphic object as a function and then return the size afterwards. So that's kind of how we can dynamically deal with different types in different ways. Next, I'm going to go over algebraic data types and kind of handling of exceptions and how we changed how we were handling exceptions to gain around a 20% throughput increase for our obfuscation standardized app. Because it's self-service and we can be dealing with a lot of different things and there's a lot of different stages to this application. There was a lot of places we were initially throwing exceptions, which are circled in this diagram. It's created with Google Cloud Profiler, I believe, if anyone has that question, and you can kind of see we're throwing exceptions in a lot of different places. The reason why that's bad is that collecting stack traces is quite an expensive operation. It makes the control flow of the whole application harder to follow. It means you have a lot of different types of exceptions being thrown in a lot of different places, and it's hard to track down specific issues when you're trying to debug. So first I'm just going to briefly cover algebraic data types, ADTs. It's a data type used to structure data within your application. They don't really provide any additional functionality, and because of that, they don't have any additional dependencies, so you can share them between modules or different applications with very, very little effort. There's three different types. There's a sum type, which allows you to model a type which can assume multiple different values. Simple example is the weather one we have here. Seal trait weather can be one of those case objects. Sunny, windy, rainy, cloudy, or foggy. The reason we use seal traits is for, I think it's called excessive exhaustive checking in compile time. So if you're doing pattern matching on a sealed trait weather or any of its inheritance, then your compiler will have a go at you at compile time. The second type is a product type, which you use to model data containing other data. An example is one down here at the bottom, forecast request. It has a two parameters string, both of them strings, country and city. Some of the benefits are you still get all of the unapply functionality of case classes. So you can see here our forecast request for South Africa, Cape Town, can be unapplied to a country and city quite easily just with one line. The third is just a hybrid. It's just a combination of the two, and that's kind of what we used going downstream. So here's a brief little example of kind of what our code was looking like before with our seal trait transformation error. It's extending just the exception, based on Scala exception, and we have a specific type, which is our missing JSON field error defined in the middle. So here would be a piece of our code that might be throwing an error. So we're trying to basically look for a specific field in a JSON document, and if that field happened to return a none, because Focus can return an option, we'd get us that and throw a wrapped exception of the JSON and just be done with it there. Going forward, we essentially removed the extension on exception and still keeping our custom missing JSON field error, but now our JSON field function returns an option of either our missing JSON object or the actual transformed JSON. So how did we then deal with this downstream? So at the end of our stream, we had a filtering function that essentially splits up the different types of exceptions based on severity and kind of how we want to handle them, and pumps them into an akka streams custom graph DSL that we built here. And essentially what that does is it allows us to filter out certain exceptions, deal with certain exceptions in some ways, and deal with some certain exceptions in other ways. So for example here with our DLQ partition exception, so if it comes through our filter onto that partition, it will log a transformation error, create and publish a DLQ message, and then merge back to the end of the stream so the message can be acknowledged and some metrics can be published. But for an obfuscation failure exception, we simply actually throw the exception and then merge back to the rest of the stream, but it probably wouldn't make it there because it would actually fail the feed and the whole app will start itself again. So what did we see side effects wise? This is the after snapshot of Google Cloud Profiler, and highlighted are the two places that we're now currently only throwing exceptions. This is a side-by-side graph of two different runs of the same test with the same data going through the same hardware, and the y-axis is a little bit messed up unfortunately, so it doesn't look quite as impressive on the graph, but the stats on the side show before we were using about 75 CPU credits for the test, and afterwards we were using about 51, so we netted about 30% less CPU usage for that test. And throughput-wise, we were getting about 7.6 thousand records a second. on our previous example, and then with the exception fix, we were netting about 9.1 thousand records a second, which is the 20% throughput increase shown in the beginning of the slides. Cool. I'm just going to hand over to Chris now.
Thank you, Tom. Hi guys, my name is Chris. I'm a developer working at Sky for the last 2.5 years. The same team as Daniele and Tom, so we look after the applications that ingest data into our platform. So I'm going to be talking about Chewbacca today. Before I do that, can I get a show of hands? How many people have actually used akka or anything from the akka ecosystem? Okay, encouraging. How many people have used akka streams in production? Okay, quite a few, good. So hopefully you guys are going to find it quite interesting. Those of you who don't, I hope you're going to find it at least inspirational. So, today we're going to be talking about what is Chewbacca, the main abstractions. I'm going to show you some code. We're going to see how we use config in a declarative manner. We're going to talk a little bit about the metrics and the future of Chewbacca. So without further ado, what is Chewbacca and what does it do besides having a cool name? Chewbacca is a set of connectors that we use for data ingestion. It's built on top of akka streams, and in particular alpaca. It's being developed internally at Sky, and it has been battle tested for over 2 years now in production. So we're quite happy with it. That's why we're showing it to you. It comes with some nice benefits. So the main one is the message delivery guarantees that it gives you, and here we're talking about at least once delivery semantics. It's quite simple to understand. You will see some well-defined abstractions and some modular architecture. It gives you hooks that allows you to control termination of your stream. The metrics are treated as a first-class citizen, and you will see what I'm talking about. And you have the ability to add or pass through metadata into your stream. What it does not do, it's not built for exactly once processing semantics. So within our platform, duplicates are generally acceptable. They don't happen frequently, but when they do, it's not the end of the world. It's not necessarily built for ultra-low latency. You can achieve low latency, but this obviously comes with the trade-off of sacrificing efficiency. So, going back to the diagram that Danny showed you, where do we use Chewbacca within our pipeline? You can see with the red arrow where Chewbacca is currently used, so it's obviously heavily involved in ingesting from various origins and different formats. And then it's also being used by the disaster recovery applications that we have. With the green arrow, so you see right at the end, it's something we're currently developing, so it's a connector which is going to be reading from PubSub other messages and going to be persisting into our data store in BigQuery. So, the main concepts with Chewbacca. First of all, we have the origin, which knows how to bring the data into your stream, and it's essentially an orchestrator which controls when we acknowledge the message back. And this is what gives us the at least once delivery semantics. The formatter knows how to convert from the input format to the format of your choice. The destination knows how to persist data into your choice of storage. The message you can see is type parameterized. It takes the arg, which we're going to talk about that, and a value. Then we have the concept of the direction. So what I showed you before, this is the ingest flow. So for us, ingest is when we essentially connect to an external source and bring the data internally. The opposite flow, we call it outgest. I'm not even sure this is a word. But you can think of it as we essentially ingest internal data and we publish that data externally. So that could be another team within Sky, or it could be an external company or whatever. And then we have the progress stacker factory, which is a nice abstraction for capturing and recording metrics. And you will see about that later. So, jumping into the origin. This is by far the most interesting component. We convert everything into a stream, even origins of batching nature, and that gives us the benefits of akka streams, like backpressuring, for example. bounded resource usage, fault recovery. And we have the capability to present useful information through our stream. We support both streaming and batching nature, although the semantics are slightly different. And essentially, you can think of an origin as a source shape, and the source shape here is a reference to an akka stream graph. And essentially, that graph uses the formatter and the destination as flows. Very importantly, it acknowledges at the end, once the message is it's correctly processed, and exposes a materialized value. And basically, this is how it looks like. So with the pink box, and my wife will tell you I'm horrible at colors, but with the pink box, we have typically 95% of the time, this is an alpaca connector, so this is our source. For those of you who don't know, a source would have exactly one output. So this brings the message into a stream. With the green boxes, we have the flows. So a flow is something that has typically one input and one output. So you see the messages are going through the formatter, the destination, and finally the item. Now this graph emits origin messages, which you see with the blue arrow, and the materialized value is with the yellow arrow. It's of future cancelable, where cancelable here it's an akka actor cancelable. My wife's laughing. So, how does the origin trait look like? And this is not the entire code, but just the interesting bits. So you would have to implement the input type. So this is the messages that are gonna be coming into your stream. Normally you would get that from the alpaca connector. The akka type, which is usually an identifier, so most of the cases this would be a string. For example, if you had a Kafka origin, the akka would probably be the offset of the Kafka message. The origin message, which is what the graph emits with a blue arrow, as you can see, it's a tape alias to the message case class. And you can see at the bottom the message case class, and you see the context. This allows us to essentially pass through useful information like timers and metadata. The akka identifier and the value, which is typically the message payload. Lastly, the entry point to our stream is the asSource method. And you can see here, this method takes the formatter and the destination as input, and implicitly takes the progress tracker factory for recording and capturing the metrics. And this gives you back a source, which emits origin messages, and the materialized value, which is the future cancelable. So, we said we support both streaming and batch nature. I'm going to start with batch origin. This would usually want or need some form of a trigger, for example, a periodic tick. You can decide which exceptions you want to ignore, because you might not want to block your stream. Importantly, you only want to act once at the end, once you have securely processed all the messages. For file-based origins, which is a type of batch origin dealing with files, we also support manifest files, decryption, unarchiving, and decompression. And this is how the batch origin trait looks like. So, interesting bits here is if I can highlight, yes, the trigger method, which gives you back a trigger, and you will see what this looks like. And then we have, if you want to show up, the ignoring continue, the hooks basically that allow you to basically define how you want to treat your exceptions, and these are implemented as parsing functions from throwable to throwable. This is what the trigger trait looks like. Importantly, because that's usually the entry point to your origin, to your stream, the items with ACK would still give you back a source. This emits item with ACK messages, which you can see at the bottom. Think of, in the case of a file-based origin, which I think is the simplest one to understand, the item would be the file, the ACK would be a unique identifier, so that would be the file name, if that's unique. And then you have hooks that let you decide how to implement ACKing and not ACKing. This is an example. I'm going to be slow on that. This is an example of how we process everything and we acknowledge at the end. So starting with our trigger, and remember the items with ACKs gives you back a source. We flat map concat that. and that essentially gives us the item itself, which is the file. Now, in line 4, in message events, what we get there, and I have omitted quite a lot of code, but what we get essentially is the contents of the file, like all the lines of the file, as a source, which have already gone through a formatter and a destination. So you have the output there formatted. This is then mapped as a write, so you have all the lines of the file, all the file contents as writes, and then in the end, you concatenate a single source where the element is coming, it's the identifier, the akka identifier from the item. So that will be the file name. So you have all the file contents as writes, and then in the end you have a left, which is essentially the file name. And as you can see in the last step, the collect one, once you basically see a left, you come across a left, then you do the acknowledgement, otherwise you return future successful. Now, in terms of the streaming origin properties, here we're talking about more frequent flow. In some cases, it could be like almost constant. Normally with akka streams, we pull when there is demand downstream. However, we also support windowing. It's very important that we don't want to block on exceptions. We want the stream to carry on, so we would normally acknowledge these messages back and raise alerts, and we would retrospectively act on these alerts because we don't want to block the stream. And we can act per element, but for efficiency, we batch the acknowledgements. And the streaming origin has also some interesting properties. So you see the inputs method that gives you a source of that emits input messages. So typically, this is where you would use your alpaca connector, maybe map the materialized value to get future cancelable back if it's not provided already. And then the act from input allows you to decide what identifier to use from the input message as the acknowledgement identifier. And the input to messages allows you from the input message to go into a list of messages that the source will emit. So, in terms of how the code looks like, especially the vanilla use case for streaming origins is simpler than batch. So we can see the messages, the inputs would give you a source, this would go into the formatter, then the destination, finally the adder. These are all implemented as flows. In terms of what we have implemented so far, in terms of origin connectors, we have the file-based ones like S3, GCS, and SFTP. We have the streaming ones like PubSub, Kafka, and SQS, and some other like BigQuery and pulling from HTTP APIs. In terms of the trigger connectors that we have implemented, we have quite a few: SQS, PubSub, Firestore, and more. Next component, the formatter. The formatter is implemented as a flow, as we said before, and it knows how to convert from the format that you get into the format of your choice. We usually convert either to byte string or to JSON. Some of the example formatters include ADT to JSON and CSV to JSON. Similar to the formatter, the destination is implemented as a flow. Some of the ones we have implemented so far are file-based ones, streaming ones like PubSub and Kafka, Firestore, and more. How do we instantiate these classes? So we use typeset config, which is written in Hocon, and then we use pure config to load this config into configuration case classes. This live in the application, and from there we can instantiate the Chewbacca classes that you saw, the abstractions that you saw. This is an example of how the feed config looks like. So we see the feed has a name, which uniquely identifies it, but then you can see the sections, the origin, the formatter, the destination. These all map to these Chewbacca abstractions that I have been talking so far. So all of that will be loaded with pure config into configuration case classes, and from there we would create our Chewbacca origins, formatters, and destinations. Quick note on the stream metrics. So the streams, Chewbacca itself, we said, and that metrics are treated as a first-class citizen. the streams will give you metrics basically. Now, these metrics we use to power our dashboards, to create alerts off the back of those, and for debugging. Now, all of this is being made available through the Progress Tracker Factory, or in short, PTF abstraction. This exposes counters and various other little things. But more importantly, it gives you metrics of your streams. For example, how many elements have gone through your stream. And it gives you checkpoint metrics. So checkpoint metrics is stuff like how much time does a particular operator in my stream spend back pressuring versus actually processing something and emitting downstream. So you could use that to find hotspots or bottlenecks in your stream. And you can use your own choice of instrumentation toolkit to plug into it. This is how the trait looks like. It's a cut-down version, focusing on the counter here. You can see the counter flow, an example of how you get counter metrics for your flow, like how many elements have gone through your particular operator in your stream. And then the checkpoint flow, if enabled, would give you all these back pressuring metrics that I just mentioned. This is an example of how these metrics translate or map into our dashboards. So we can see here, I hope you can see that, here we have a streaming origin. I think this is the SkyQ watch events. I think that's a Kafka origin. And we can see the 4 sections. These correspond to the little boxes that I showed you earlier in the graph. So we can see the read is essentially what the Alpaca connector brings in, so what data we bring into our stream. The formatted is data going through the formatter, the published is messages going through the destination, and the ACK are messages going through the ACKer. This is an example of a batch origin. Now, you might notice that the read and ACK section, the graph is slightly different from the formatter and published, and you might ask why. So this is the Adobe Analytics data feeds, and these are file-based origins, and they use a PubSub trigger. Essentially, that means when there is a file landed on a GCS bucket or an S3 bucket, a notification is being generated. And then this origin is listening for these notifications and goes and processes these files. So essentially, what the read or the ACK represents in here is that a new notification has come into the topic. So go on and consume that, process it through the formatter and the destination. You see a few thousand or million rows in there. Finally, add the notification back to the subscription. All right, so going forward, as I showed you with the green arrow on the diagram, we are already developing a new component that's going to be reading Avro messages from PubSub and persisting into BigQuery. As we ingest more feeds, whenever there is a need for a new connector, we will be obviously developing that. However, more importantly, we're interested in open sourcing this. So if you found it useful generally, just come and talk to us after the presentation. Thank you all very much for listening to us, and may the force be with you.